Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the nanoHUB-U course, Thermal Energy at the Nanoscale. I'm Tim Fisher, and we're in the middle of week 4, which is on Landauer transport theory. And today we're actually going to cover something I've been talking about periodically throughout the course, and that's the subject of the number of modes. Now back to this image, which I've shown many times. Our goal is to understand how heat flows from a hot thing to a cold thing through a device, and we'd like to maybe design that device to be a certain size and understand what happens if we change the size or maybe the crystal structure. And we said that we could express the rate of heat flow, that would be in units of watts, as an integral, in this case over frequency space. So this is kind of specialized toward phonons, but we could do a frequency space integral for electrons also. And the first term in the summation was this number of modes. And we haven't really described what it is because we had to build some of the framework for it and some of the foundation to understand what it really means. And that's what we're going to do today. We finished the last lecture talking about heat flux for phonons and electrons, and I'm showing here the expressions for phonons. And so this is the heat flux. Again, that's heat flow rate per unit area, whatever area means in the dimensionality. In 3 dimensions, it's the area that we're used to thinking about, but in 2D it would be a line length, and in 1D it doesn't really, there is no such thing as area. But we expressed this integral as a collection of terms, and we did it very intentionally. We kind of expressed this velocity as within a group of other constants, and it turns out that those constants actually are needed to say that's the average velocity in the direction of transport. Okay, and the rest of the terms are energy, transmission function, distribution function difference, and so forth. And most of those, except for the transmission function we've covered, we're going to have to wait another week for the transmission function. So let's look at this in a couple of dimensionalities. The heat flux, again, if I had a one-dimensional system, the heat flux is the same as the heat flow rate. They both have units of watts because there's no area basis. But for a two-dimensional system, let's say it has a width of W, then I would want to scale the heat flux by that width W, or the heat flow rate, rather, Q, by that width W, and that would give me a heat flux. And so generally speaking with a flux, if I multiply by a dimensional quantity like area or width in a two-dimensional problem, then I'll just linearly scale the heat flow rate with that dimensionality. In 3-dimension, it's the usual Q divided by area. We're going to focus our attention on a couple of these different dimensions to really understand what's going on with this number of modes. And we're going to start with a 2D problem. So I'm going to do this part of the expression and this part of the explanation by deduction. So we're going to say that we're going to postulate that the heat flow rate Q can be expressed as this collection of terms. And remember that first term was M. And now we're going to say that in 2D, if I wanted to express the heat flow rate, we already have an expression for heat flux, that's J sub Q, then what we would do is we'd multiply it by W, and that would give us the total Q. So we go ahead and do that, and we find that by comparing these two equations, which are very similar, the only differences actually lie in that kind of the first set of terms, and that set of terms, by inspection, we have to have that the factor M, which we're calling the number of modes, is a product of the width, the group velocity, the density of states, and we're going to say that it's actually times a multiple of 2, and so we're going to break that 2, and we're going to say that's going to equal pi divided by pi, and the reason we do that, again, is we're going to get back to that average velocity in the direction of transport. That's what 2 over pi does for us, because 2 over pi is the average of cosine theta in the x direction. And so what we find is that we can express this number of modes as a collection of width, so there's a length scale to it, there's a velocity, and in this case we'll think of that as an average velocity, and our density of states. Right now it probably doesn't look like a number of modes, it just looks like a group of terms, and so we'll explain that number of modes in a bit. We can also express the number of modes as a mode density, and so you'll see that done also in, for example, in Professor Lundström's and Professor Dada's courses on electron transport, where you can take the W as a separate term and say that the total number of modes equals W times the two-dimensional mode density. And so that you'll see that occasionally as well, and I wanted to include it here. Well, what does it mean physically? So deduction, mathematical deduction is one thing, but what does it mean physically? Well, you can think of it as, and this is the way that Professors Lundström and Dada explain it for electron transport, which also applies here. But M, first of all, we recognize is a dimensionless number. Even though it has components that have dimensions to it, it is a dimensionless number. And what it really represents is the number of bands that fit into the width of the device. What are bands that fit in the width of a device? Well, the cross-directional carriers have to be able to fit in terms of they have to have their wavelengths fit into this width. But we could have multiple of those. Now, the waves in that direction, or the elements of the waves, the components of the waves in that direction do not contribute to transport because we are interested in transport in the x direction here. But we can have a number of different wavelengths in the cross plane direction or the transverse direction. And so the smallest wave vector will be a half wave, and then the next one will be a full wavelength. Those are the only two that I've shown on this figure, but it goes on and on, so that a half wave, every half wave increment can fit into this width. And so those are the different modes. And so M is the number of those that fit into a width W of this device. Okay, and that's what essentially the number of modes represents physically. So if we go back to our two-dimensional example, again, we have the expression for the number of modes, and it depends on the width. So we would expect logically that the wider my sample is, my device is, the more modes I'd be able to fit into it. The velocity also is a factor here because the velocity has to do with the waves and their transport, even in the transverse direction, and also the density of states. So we have to, if we understand how many states can fit in that width, then that will tell us how many modes can fit, or be a component to the number of modes that can fit. So if we took a generic form, let's say that I have d, lowercase d, dimensions. M is really some area, whatever area means in the dimensionality of our problem. So in one dimension, it's just unitless. It's just one. And then we multiply that by pi times the average group velocity times the density of states in our dimensionality of interest. And so that also could be expressed as the area, this area in quotes, multiplied by the mode density. That's the M subscript dd. That's the mode density specific to a dimensionality of the problem. So again, getting back to this, now recalling our expressions for phonons, we have these densities of states. And in fact, the density of states is inversely proportional to the group velocity, and the modes and the mode densities are directly proportional to group velocity, so that term's actually going to cancel out. And you see these expressions, by the way, we've not yet made any approximation to the dispersion relation. So we're expressing these in terms of k as a function of omega. So if we just go through and do these substitutions, substitute the density of states in the various dimensions into our expression for the number of modes m, we find that in one dimension, there's one mode. Well, that should be somewhat reassuring because we would expect in a purely one-dimensional problem, only one could fit. only one thing could fit along the carrier or in the device, and so we that meets our expectations quite well. In 2 dimensions, again, the velocities will cancel, but we keep them in the expression regardless, because it's nice to kind of group that terms as the term, the average velocity. That's 2 times the group velocity divided by pi. So that's the average velocity in the direction of interest for the transport problem. In this case, that's the x direction. And then in 3 dimensions, we also have the expression. Now, what we'll often do in looking at the number of modes is we'll make a dispersion approximation, which we haven't done here yet, but we could put in, for example, a Debye approximation, and then we would have a very, very clean expression for the number of modes for phonons in these various dimensionalities. And we'll start to work with those kinds of problems as we move forward through this week. That's it for today, and thank you for your attention. We'll talk next time. Thanks.